We all think we get forces, right? A push, a pull. Simple. But what if that's just scratching the surface? In this explainer, we're going to peel back those layers and look at the elegant underlying architecture of energy that's really running the show. Okay, so picture this. We've all been there, holding a super heavy bag, maybe carrying groceries up a few flights of stairs, or just holding a weight still at the gym. Your muscles are on fire, you start to shake, it feels like you're doing a ton of work. It is exhausting.
But here's the crazy part. According to the super strict official definition in physics, if that weight isn't actually moving, the amount of work you're doing on it is zero. Absolutely nothing. Nada.
So, what gives? How is that even possible? Is physics just playing games with us? Or is there something deeper going on that our intuition is missing? Well, that very paradox is our doorway into a much more fundamental way of looking at energy.
To get to the bottom of this, we first have to realize that science is kind of using two different definitions of the word work. There's the biological one, and then there's the physics one. Let's just break it down. On the one hand, you've got biological work. See, our muscles can't just lock into place. To hold something steady, they have to constantly fire, with zillions of tiny muscle fibers twitching over and over again. And that burns a lot of energy, which is why we feel so tired. But on the other hand, you have physical work. And physics has a really simple, hardcore rule. If there's no movement, there's no work. Period.
Okay, so let's put the biology on the shelf for a minute and really dig into this super precise and, yeah, sometimes kind of weird physics definition.
So in physics, work is all about transferring energy. It happens when you apply a force that actually makes an object move a certain distance. Now, you calculate it with this formula, which is called a line integral. And I know, that looks a little scary, but stick with me, the core idea behind it is actually super simple.
It all boils down to that one little dot in the middle, between the F and the ds. That's a dot product, and it is everything. It's basically a mathematical gatekeeper that says only the part of the force that's pointing in the exact same direction as the movement gets to count as work. Any force pushing at an angle, especially one that's perpendicular, it contributes absolutely nothing.
Think about a roller coaster, right? The track itself is pushing up on the car with a massive amount of force to keep it from, falling. But that force is always at a perfect 90-degree angle to the direction the car is zooming along the track. So believe it or not, the track itself does zero work. It's just there to guide the ride. The only force that's actually doing the work to make the car speed up and slow down is good old gravity. And this whole idea that some forces do work, while others just come along for the ride, well, it opens the door to this incredibly powerful and elegant shortcut for understanding the universe, the whole concept of potential energy.
For certain special forces, like gravity, physicists call them conservative forces, something really amazing happens. The amount of work needed to move something between 2 points is always the same, no matter how you get there. You could take the direct, straight-shot path A, or you could take the crazy, winding, scenic route B. It doesn't matter. The work done by gravity is identical. All that matters is where you start and where you end.
So, because the journey doesn't matter, we can do something really cool. We can just assign a number, a value, to every single point in space. We call this potential energy, or U. It's like having an energy map of the universe. So the work done by gravity when a book falls off a shelf is just the difference in the potential energy number between the shelf and the floor. Simple as that.
And this is where it all comes together, leading to one of the most powerful and fundamental laws in all of science, the conservation of mechanical energy. It just means that the sum of an object's energy of motion, that's its kinetic energy T, and its stored energy of position, its potential energy U, that sum is always constant. If one goes up, the other has to go down. It's a perfect balancing act. Okay, this all sounds really nice and neat, doesn't it? A perfectly balanced system. But I know what you're thinking. What about messy, real-world stuff like friction? It really seems like it breaks this beautiful law. I mean, think about it. You slide a book across a table. It's moving, it has kinetic energy, and then it just stops. That energy wasn't conserved. It just vanished. Poof, gone. It seems like our elegant T plus U equals constant rule is totally broken. So where the heck did that energy go? Well, the secret is you have to change your perspective. You have to zoom way in. At our big macro scale, yeah, the energy looks like it just disappears. But if you could zoom down to the micro scale, the atomic level, you'd see the truth. That organized, unified kinetic energy of the sliding block hasn't been destroyed. It's just been transformed, repackaged into the messy, chaotic, jiggling kinetic energy of individual atoms.
And we have a name for that microscopic jiggling. We call it heat. Nothing was ever lost.
And that right there is a huge, huge revelation. What this means is that there aren't really any non-conservative forces. Friction isn't some fundamental force that goes around destroying energy. It's a large-scale illusion. The energy is always conserved. You just have to know where to look for it. We only think energy is lost because we can't see the tiny atomic chaos it turns into.
So once you start seeing the world this way, through this lens of energy, it gives you this amazing blueprint for how forces actually work across the board.
So, forget about mysterious pushes or pulls. Instead, I want you to picture potential energy as a landscape, like a 3D map with hills and valleys. In this view, a force is nothing more than nature's way of saying, roll downhill along the steepest path. An object just follows the slope, what physicists call the gradient of the energy landscape. That's it. That's what a force is.
And look, this isn't just some cute metaphor. This energy blueprint is the deep mathematical reality of how our universe is built. You can look at the fundamental forces like gravitation and electricity, and you see the exact same structure. A source creates a field, the field defines the potential landscape, and the landscape tells you the force. It's the same blueprint, just running on different operating systems.
So, when you step back and look at the whole picture, it all comes back to this one perfect, unbroken law. From the dance of stars inside a galaxy down to the vibrations of atoms in a crystal, the total energy of any closed system is perfectly, eternally constant. Any energy that seems lost is just an illusion, a failure of our human scale point of view.
Which kind of leaves you wondering, doesn't it? If something as real and intuitive as the energy lost to friction turns out to be just an illusion of our limited perspective, what other fundamental ideas we have about the universe might also be just a matter of not being able to see the full picture?